as an example, we will discuss here the magnetic field surrounding a state conducting Y. Conducting T-I-N-G, conducting Y. Okay, so in this case, we want to calculate the magnetic field that generates from the current that passing through a straight conducting Y. Okay, at the point P here. Okay, at the point P here. And this point P is at the distance A from the Y. Okay, this distance A from the Y. And if we draw a line from the point P to the starting point of the Y, we have the angle θ1, okay, between this line and the line perpendicular, line from P perpendicular to the Y. And if we draw this line to the end point, we have the angle θ2 between this line and the line perpendicular to the Y. Okay. We set our reference coordinate x, y, and z like this. X point in this direction, y point upward in this direction, and z point out from the screen or from the paper. Okay, and if we write the unit vector, so this is the direction of the unit vector I, this is the direction of the unit vector j, and this is the direction of the unit vector k. Okay. Since from the Biot-Savart law, to calculate the magnetic field B at point P, we will divide the Y into a small segment and calculate the magnetic field from each segment, and then sum it up to get the total magnetic field here. So let's see that what is the magnetic field from this segment. From the Biot-Savart law, we have that dB is equal to mu 0 over 4 pi I ds cross r over r squared. Okay, so if we have the segment ds here, this is the length vector ds, and the unit vector r is the unit vector that point from this segment to point P, and r is the distance from this segment to point P, this r. Okay, now let us first look at the vector ds cross r. ds cross r here. If we say that the length of this segment is ds, but as the ds is along the x direction, we will say that the length of the ds is equal to dx. This is just a name. You can use any name you like, but for our convenience, since the straight line are on the x-axis, the straight line is on the x-axis, so we name the length of ds as dx. Okay, and when we do the cross product, ds cross r is a unit vector, so the magnitude of r is 1. So it means that the magnitude of ds cross r is the magnitude of ds times sine of the angle between vector r and ds. And this angle is here, right? May write this is phi. So we must have that the magnitude of ds cross r is the dx psi phi, right? This is the magnitude of ds cross r, and the direction of ds cross r, we can use the right hand rule. If you point your forefinger in the direction of ds and r, the unit vector r, point out from your palm, you can see that the magnitude of the direction of the dB, okay, or the not dB now, but the direction of ds cross r is the direction of your thumb that is point out of the paper or of the screen. So in this case, we have that ds cross r point out of the screen. Okay, this is the direction of ds cross r. Okay. So when we write this ds cross r, when we look when we know that ds cross r point out of the paper of point out of the screen, you can see that the direction of ds cross r is the same direction as the unit vector k, right? From our definition of the left-hand angle, we have the c angle or z angle point out of the plane. So the unit vector k point out of the plane. So we have the direction of ds cross r is the same as k. Okay. So we can write the ds cross r as the magnitude of ds cross r times the unit vector in this direction. So it means that it is a dx psi phi times k. But we can see that from this triangle, phi is equal to pi over 2 minus theta. So we have that dx psi phi is equal to dx psi pi over 2 minus theta. And from the trigonometry, the trigonometry identity, we have that sine pi over 2 minus theta is equal to cos theta. Okay, is equal to cos theta. So we can write that ds cross r is equal to the dx, which is the length of this segment, times cos theta times k. You can see that every segment on this y, for example, if you look at the vector ds here, and now we have if we look at this segment ds here, you can see that now the unit vector r we point in this direction, and again the dB we point out of the plane, right? If you put your forefinger in the direction of ds and unit vector r point out from your palm, you can see that ds cos r we point in the direction of your thumb, which is the direction of the unit vector k. So it means that for every segment on this y, the direction of the magnetic field that produced by each segment will point to the same direction, which is the direction of the unit vector k. So it means that we don't have to worry about the direction of the magnetic field. We know that the total magnetic field must point in the direction of the unit vector k. This is because all segments of the y produce the magnetic field that point in the direction of unit vector k. And when you sum up the magnetic field, it must point out in the direction of unit vector k. So now we will look at the magnitude of the magnetic field only, because we already know the direction of the magnetic field. Okay, and how can we calculate the magnitude of the magnetic field? We have this formula for the magnetic field, and if we write the magnitude only, we have that dB is equal to exit mu naught 4 pi is I, you must have I here. Okay, this is mu 0 or mu naught 4 pi I dx cos theta over r square. Okay, so we have the magnitude of dB like this. We know that the direction is always the unit vector k. Now we want to sum up this dB using the integral. Okay, but before we do that, we have to rearrange the variable when we do the integral to be the same. Here we have the variable which is x, theta, and r. So we will change all of these three variables to be one variable, and we will choose here the theta as our variable. So we will write all of these variables into the theta. First, we have that r is related to theta from this relation, that is a is equal to r cos theta. If we look at this figure, this is r and this is a. Okay, so you can see that a is equal to r cos theta, or we may write r is equal to a over cos theta. Okay. Also, we can see that x is equal to the minus a tan theta. Here, x is the position of the segment of the y, and we define the position that x equal to 0 is the position that when we draw the line from P perpendicular to the y, we have this point as x is equal to 0. So the position of this segment is measured from this x, from this position, reference position x equal to 0, and this is the position x. And you can see that for the y segment in this here, x is negative. For the y segment here, x is positive. Okay. We can also write x in terms of theta by looking at the trigonometry function. Okay, you can see that let's write here, tan theta is equal to x over a, right? Tan theta is equal to x over a. But in this case, we have to be careful about the sign. Because we know that x here is negative. Okay, in this, for this segment, here is negative. But in our system of, for the angle theta, we say that this angle theta is positive when we measure the angle theta in the clockwise direction. We say that this is positive. Okay, so we have that this tan theta is positive, right? But x is negative. So to make this equal, the right hand side, the left hand side and the right hand side equal, we must put the negative sign here. It means that x itself is negative for this segment, and this x time, or when we put the negative sign here, it means the minus a is positive. A is positive by definition, is the distance. Okay, and tan theta here for this segment is positive. So we have that we can write that this tan theta is equal to the minus x over a. If we look at this segment, in this segment x is positive, but the angle theta in this direction is negative. So we have tan theta is negative here, x is positive, so we have to put the negative side here to make two sides, we can say that two sides are equal. Okay, so we have this tan theta equal to the minus x over a, or we can see that x is equal to the minus a tan theta. Then we can write the differential of x dx, which is dx, is equal to a. In fact, it is dx equal to the minus a d tan theta. And when you find the differential of tan theta is equal to the sec or secant square, we can say that it's sec square theta d theta. Okay, you can learn, or you can see this, or I think you already learned this from your calculus course. So we have that dx is equal to minus a sec square theta d theta, and since from the definition sec is a secant function or sec function is a reciprocal of the cos or cosine function, so we have that dx is equal to the minus a d theta over cos square theta. Now you can see that we have dx, we can write dx in terms of theta, we can write r in terms of theta. So if we put all of this into the Biot-Savart law, we will have this. In fact, you have to do some algebra here. You put dx equal to this into this dx, and you put r equal to a over cos theta, and you square it and put it here, or here for the magnitude, and then some cos function cancel, and also a cancel. Okay, no, not all a cancel, I think I missed some a. Okay, you must have a here. Okay, you must have a here. So if you do the detailed calculation, you will find that this dB is equal to the minus mu 0 I over 4 pi a cos theta d theta. Now you have the magnetic field from a segment. What you have to do next is to sum up the magnetic field for every segment by doing the integral. Here the integral here is, since we use the variable for the integration as a theta, so the limit of integration is the angle theta from the starting point, which is the theta 1 here, and ending point, which is the theta 2 here. When you do the numerical calculation, you may have to be careful about the sign of the theta 1 and theta 2, because by definition, we let the theta 1 to be positive and theta 2 to be negative. So when you put the value of the limit here, you must put the theta 1 as a positive and the theta 2 as a negative. Okay. Now, we have the formula to calculate the magnetic field. Okay. Again, since this mu 0 I 4 pi and a are constants, so we can take this all constant out of the integration and do the integration of cos theta d theta, and the integration of cos theta d theta is sin theta. Okay, because differentiate of sin theta is cos theta, so integration of cos theta is sin theta. And since we do the definite integral, so we have to put the limit of integral here. which mean that this term sine theta from theta 1 to theta 2 is equal to sine theta 2 minus sine theta 1. Okay. Now we can put this negative sign to this term, which we can swap the order of sine theta 1 and theta 2. So finally we have that the magnetic field is equal to the mu 0 I over 4 pi a of sine theta 1 minus sine theta 2. You can see that the order of sine theta 2 and sine theta 1 swap because of this negative sign. So we have the closed form of the magnitude of the magnetic field like this. The direction, of course, is the direction of the unit vector k. Okay. Now, the interesting case is that if we have a very long y, okay, if we have a very long y, when we say that it's very long y, it means that if you compare the distance a with the distance from two endpoints, okay, we have x equal to 0 here, and the distance from this endpoint to x0 and this from x0 to this endpoint is much longer than a. So you will see that we will have that the angle theta 1 here and the angle theta 2 here will approach pi over 2, right? This is a pi over 2. This is pi over 2, and this is minus pi over 2, right? Because we define the positive angle in this direction, so negative angle in this direction. And when the y is very long, you can see that the angle theta 1 will approach pi over 2, and the angle theta 2 will approach minus pi over 2. So we can say that for a very long y, theta 1 will approach pi over 2, theta 2 will approach minus pi over 2. And when we substitute this value into this formula, you can see that sine of pi over 2 is 1, and sine of minus pi over 2 is minus 1. Okay, so we have that sine theta 1 minus sine theta 2 is equal to 1 minus 1, which is equal to 2, right? And then we substitute this result into this formula. Okay, and finally we have the magnetic field is equal to mu 0 I over 2 pi a, because these two will cancel with not cancel. 2, we have 2 here and we have 4 here, and 2 over 4 is 2, 1 over 2. So we have that b is equal to mu 0 I over 2 pi a. Okay, this formula is quite important that we will use this again when we discuss the Ampere's law. Okay, in Ampere's law we will see that we can calculate the magnetic field from this long straight line very easily, much easier than using the Biot-Savart law.